In our previous videos, we were looking at discrete probability distributions, like the binomial distribution. We talked about negative binomial, hypergeometric, and Poisson. In these videos coming up, we're going to look at continuous probability distributions, uniform and the normal distribution. When we talked about discrete distributions, we were creating a probability mass function, a PMF. With continuous distributions, we create a PDF, a probability density function. So here on the right, you can see a probability density function. Unlike the probability mass function, it's kind of smoothed out to show the fact that with a continuous distribution, we are focusing not on the probability of a specific outcome, but on a range or interval of outcomes. So in this particular example here on the right, values of random variables, we wouldn't be looking at what's the probability that x is equal to 12. We might be looking at a range. What's the probability that x is equal to 12 to 14? Or the probability that x is less than 8. Okay, so let's take a look at continuous distributions. When you have a probability distribution function for a continuous distribution, there are a couple of characteristics or properties we need to know. The total area under the curve equals 1. This is the same as the probability mass function adding up all the different probabilities to equal 1, because if you have identified every different possible outcome, so we are collectively exhaustive, then we've represented everything, so 100% of the outcomes. The same thing is true with this continuous distribution. We're representing that as a smooth curve, but it's showing here is the events of some numbers between 14 and 16. Here's the probability of 6 to 8. And so the area under this curve is all the possible outcomes and their probabilities, so it must equal 1. The probability of being between A and B is the area under the curve from A to B. So if we want to know the probability that x is less than 8, let's go back to using our pencil here. We want to know the probability that x is less than 8. Then what we would do is we're looking for all this area here under the curve. Okay. This is going to become particularly important later when we get to our inferential statistics, and we are looking at p-values and alpha to determine whether or not we have statistically significant difference. So we're building up to get to these statistical tests to say, is the treatment different from the placebo in terms of the impact it's having? So we're getting there. It may be kind of hard to see that end goal as we go through some of these details here. But the area under the curve has to equal 1, and if we want to know the range, if we want to know the probability of getting between 12 and 14, we would look for that area under the curve from 12 to 14. What's the probability that x is equal to a? Well, the probability of any single number is going to be 0. And that's because if we have continuous measurement, we can have all kinds of fractions. So the likelihood of getting exactly one specific number, 12.0001, is 0%. That's why we're looking at intervals or ranges of numbers, not a specific number, because the probability of exactly one number with every decimal point is going to be nothing. Okay? All right, so examples of probability distribution functions. I just looked at PDF and my mind went blank and I couldn't remember what PDF standed for. Probability distribution functions, PDF, examples of them. A normal distribution, that's the one on the left. The normal distribution is the bell-shaped curve. So here we have the expected value, mu. This here shows you that within one standard deviation, we have 68% of the values. Within 2 standard deviations, we have 95% of the values. Within 3 standard deviations, we have 99.7% of the values. That's the empirical rule that we'll use a lot throughout our videos here. So a normal distribution. It has a center where the mean, the median, and the mode are the same. It is symmetrical in terms of its tails. Another type of continuous distribution is a uniform distribution. That's where everything in between the max and the min have an equally likely probability of occurring. Okay, so whereas the normal distribution has this center, the most likely result is right there in the middle where the mean, the median, and the mode are all equal. The uniform distribution, everything is equally likely between the min and the max. Okay, just like we talked about before, we can find a cumulative distribution function. So remember, a cumulative distribution function adds up all the probabilities that are below it, so that when a cumulative distribution function, it's going to go from 0 to 100% as we look at what's the probability of everything less than that particular number. So with a cumulative distribution function for a continuous distribution, what we're getting is we're getting the probability of the area under the curve. And so what we're doing is actually differentiating using calculus, finding that area under the curve. We won't do calculus in this. So relationship between a PDF and a CDF. So here's our probability density function. Here we are at mu, and we see this region here is shaded in. That shaded in is 50%, and so that value here at CDF at that same number is going to be 0.5. So what it's doing is representing the amount of shading under the curve, because a cumulative density function says what percentage is below that number. And so if we're here, whatever number this is, the shaded area amount here, that's going to be the value. Not this number, but the shaded amount is going to be this value. Okay, and so once we get to here, we now have completed the entire 100%, and so that's why we get a 1 for the cumulative density function. Okay. When it comes to expected values of continuous distribution functions, the expected value of a continuous random variable is the population mean, the average in the long run of the random variable, and can be found through the use of this function here, finding mu. From visual inspection of the random variable, the center is going to be your expected value if you have a normal distribution. Okay. And I'm just glossing over this because, again, we're not doing calculus in these videos. So we'll talk later about how to get there. But really, if you're looking at your normal distribution, it's going to be that center of the distribution. All right, so let's look at an example here. A psychologist studied the length of time X in seconds is required for, figure out where this is. Okay, the psychologist studied the length of time in seconds required for completion of a project by first graders in a large city. The probability distribution is as follows. We want to know what percentage of students completed the project in less than 60 seconds. So to figure out the probability that they finished in less than 60 seconds, we need to add together 0.393 plus 0.239. That will give us the probability that they completed in less than 60 seconds. So the area under the probability density function is giving us that area. What percentage of students completed the project between 60 and 120 seconds? To find that, we would go from 60 to 120. So that's 0.145 plus 0.088. Okay. What percentage of students completed the project in more than 180 seconds? Here's 180, right? We need to know what is there, what is left. In this particular image, what do we know? Well, we don't have a number listed there, but you could figure out what it is, because what we know is that 100% is below the curve. So you could take 1 minus and find the probability that x is less than 180, which we would get by adding up all these numbers. So if we added 0.393 plus 0.239 plus 145 plus 0.088 plus 0.053 plus 0.032, that's this probability that x is less than 180. Subtract that from 1, and we would get the probability the project is more than 180 seconds. So now suppose the psychologist is going to give the problem to a new group of first graders. She's going to allow them 2 minutes. About what percentage of these children are not expected to complete the project? So how many are going to take more than 2 minutes? Well, what is the probability that it takes more than 120 seconds? So we look here at 120, everything to the right, including that unknown. We would need to know that information to know the probability that are going to take more than 2 minutes.